Hi and welcome to this Leaving Cert Applied Maths video. Today we're talking about uniform acceleration and specifically we're going to look at horizontal linear motion. So this is our first video of 3 which focus on uniform acceleration, and in this video we're going to look at some two-body questions and some common initial velocity questions. So this is suitable for both ordinary levels and higher levels. We're going to look at questions from both papers. So let's start with some two-body questions. So here are some key ideas to keep in mind when we're looking at two-body questions. So the first one is that the greatest gap between two particles occurs when their speeds are equal. Now, I just need to caveat that by saying that's when the back particle or back body is catching up on the one in front of it, okay? If the one in front is going on ahead and will continue to get further and further away, then the greatest gap will effectively go to infinity if it continued that pattern. So here we're talking about the greatest gap when the body behind is catching up on the particle in front. The second thing is, if two particles move towards each other, which we have seen on some of our exam questions, that means that the sum of their distance will be the total distance in the question. Often when we think about bodies meeting initially, or maybe straight away, our brain goes to when they meet, their distance traveled will be the same. But that's only true if they start at the same point. If they start at different points, and specifically if they start at different ends, then we have to think in terms of the sum of their distances. And then the trickiest one is the idea that when particles start moving at different times, we need to be very careful with how we deal with those times. So imagine we have a second particle that starts k seconds later. Okay, this means there will be less time. So think of that in terms of numbers first to really get your head around it. So if two people were to leave the same spot, but one leaves 2 hours later, when they meet, the time the second person has traveled is 2 hours less. So we just need to be really careful with that word later, because often we think of that means later. So you're adding it on. You are taking it away, because if they leave later, they have been moving for less time. So we have to take it away. We're subtracting it. Okay, so be really careful with those. So let's take a look at an ordinary level question here. This is from the 2009 paper and it's question 1. So we have a nice little diagram that goes along with this, but we're told that we have 3 points, P, Q and R, that lie on a straight level road. 2 cars, A and B, are moving towards each other on the road. Car A passes P with speed 3 meters per second and uniform acceleration 2 meters per second squared. And at the same instant, B passes R with speed 5 meters per second and uniform acceleration 4 meters per second squared. A and B pass each other at Q, which is 7 seconds later. Okay, so we have a lot of information going on here, and it says find the speed of car A and the speed of car B when it gets to Q. So the first thing we're going to do is we're going to set up our VUAST, but we are going to use some subscripts here to help us keep track of what is happening. So we have car A and we have car B. So there is VUAST for car A, and then we have VUAST for car B. So let's fill in what we know. We're looking for the speeds. So that is going to be V. It'll be the speed after a certain point. So going back to our question, car A starts with 3 meters per second and is accelerating uniformly at 2 meters per second squared. And we know that they pass each other at Q, which is 7 seconds later. So time is 7 seconds. For B, it passes or with speed 5 meters per second. The uniform acceleration is 4 meters per second squared, and then the time is still 7 seconds. So we have enough information for both of them to work out our V. We're going to use V equals U plus AT for both. So the velocity of A is going to be UA, which is 3, plus A, which is 2, times T, which is 7. So that is 2 times 7, which is 14, plus 3, which gives us 17 meters per second. For B, we have U plus AT. So 4 times 7 is 28 plus 5, 33 meters per second. So these are answers for part 1, our VA and our VB. So very straightforward. We just need to be very clear on which bit of information belongs to which car. So then the next thing they want us to work out is P to Q and R to Q. So looking at our diagram, P to Q is going to be the distance traveled by A, and then R to Q is going to be the distance traveled by B. So those two straight lines, they're telling us that is distance. So we can use the same setup we had before. I'm just now going to add in my V. What that means is we have every bit of information we could have. We're looking for S in both cases, so any formula with an S can be used. I'm going to use S equals UT plus a half AT squared. The S is on its own. That can just then be a nice bit of calculator work. So SA is equal to UT plus a half AT squared, which gives us 49 plus 21, which gives us 70 meters. SB is equal to UT plus a half AT squared. So that's 49 times 2. So that's our 98. And 98 plus our 35. And that gives us 133 meters. So there are two answers for part 2, our SA, the distance traveled by A, and our SB. Okay, so what we've been able to see here, and I'm going to put this on our diagram, is that we have 70 meters here, and for SB we have 133 meters. So we now would know the total distance from P to R if we were asked this. So part 3 tells us that car A stops accelerating at Q and continues on to R at a uniform speed. Find, correct to one place of decimal, the total time for car A to travel from P to R. So I've just cleared the screen so we have a bit more space to work. So the question is asking the total time for A to get from P to R. Now here's the thing, we already know that for A to get from P to Q takes 7 seconds. Okay, so really what we're focusing on for A is getting from Q to R. So we know that it stops accelerating and it continues at that uniform speed. Part 1 of the question told us that the velocity of A when it gets to Q was 17 meters per second. So this is now going to be the constant speed. We are welcome to use our VUAST here and it will work out absolutely perfectly. However, you can also use the DST basic formula because we have no acceleration. So either of those are absolutely fine to use. So I'm going to do VUAST and then I'll show you the other way just so you're clear to see if you can use your distance, speed, time, those basic formulas. And in particular, this one we want time, so it's going to be distance over speed, as long as there's no acceleration, so a uniform speed. So I'll actually, instead of constant, I'm going to use the words that are in this question, which is uniform speed. Uniform speed means it doesn't change. So that means it's going to start at 17. It's going to end at 17, and there is no acceleration. We know how far it travels, and that's going to be 133 meters. And then all we're looking out for is time. So you can use pretty much any formula that doesn't, we have to be careful because if you try use V equals U plus AT, and I'll just show you this very quickly. V is 17, U is 17, plus A is 0 times T, and that disappears. So it tells us 17 is 17. It's correct, but it doesn't actually get us a value for T. we're not going to use v squared equals u squared plus 2as because it doesn't have a t. So it's better for us to use s equal to ut plus a half at squared. And that for us is going to be 133 is equal to 17 times t plus a half times 0t squared. This part is going to go to 0, so time is going to be 133 divided by 17. We want our answer, the final answer, correct to 1 decimal place. So we can round this to 1 decimal place. So that's going to be 7.8 7.8 seconds, because it's time. And then our total time, because that's what they asked, because we want to go total time, and that's to get from P to R, is going to be the 7 seconds plus the 7.8 we've just worked out, which is 14.8 seconds. Now, I just want to show you what would happen if we use the DST. So time is equal to distance divided by speed. They are capital letters so as not to get confused with your S for speed and S for displacement. The distance we're talking about is the 133. The speed it's traveling is at 17, and we get exactly the same answer. So just to see that if you wanted to approach it using your DST formulas, that you can, because they are valid when we have no acceleration, when we're talking about a uniform speed. Okay, so it's not an exam question, but it is more leaning towards kind of a higher level question. So at a certain moment during a foot race, Adam is 22 meters behind Ben. So let's draw this out, because it's always good to have a visual. So here's Adam and here's Ben, and there's 22 meters between them. Adam is running at 12 meters per second and accelerating at 1 meter per second squared. Ben, who has just tied his shoe, starts from rest and accelerates at 2 meters per second squared. After how long will Adam catch up with Ben? So this is where we need to do a little bit more thinking. So let's start with our VUAST, and we'll again use our subscripts. A for Adam, B for Ben. So it works out A and B, look, body A, body B. UAST. Okay, so we fill in what we know. So for Adam, he is running at 12 meters per second. So he's kind of going, and he is accelerating at 1 meter per second squared. So then Ben has just tied his shoe. So he is starting from rest. He is accelerating more. But what will happen is Adam will catch up on Ben. And then because Ben will keep running and he's accelerating at a faster rate, he will then overtake Adam again. So we need to connect these two. So the first thing we have to understand is at a certain moment means they're both, this is happening simultaneously. So this is happening at the same time. So both of our times are going to be t. They're not different times. What will be different is the distance traveled by each. So because Ben is ahead, whatever Ben runs, by the time Adam catches up, Adam will have had to run an extra 22 meters. So imagine the situation is this, right? So Ben runs on, I'll just put a random number on it. Let's say Ben runs on an extra 10 meters, and that's the point where Adam catches up. So in order for Adam to have caught up with Ben, Adam would have also have to run that 10 meters, but equally would have had to run the 22 meters that he's behind to catch up. So whatever Ben runs, and we're going to call that X, Adam will have run the same amount plus the 22 meters to catch up on Ben. So whatever Ben runs, Adam will run that plus a 22. So that's how we're going to connect on a second variable. So we're going to connect. You're welcome to use S. Often we use X instead for displacement, especially if it's missing. So what we have here are going to be simultaneous equations. So we have no V in either. So the formula we're going to use for both is going to be S is equal to UT plus a half AT squared. So then we have the displacement or distance traveled by Adam is going to be ut plus a half at squared, and that's going to be x plus 22 equals 12t plus a half t squared, and that's going to be equation 1. And then for Ben, it's going to be ut plus a half at squared, and then that's going to be x equals t squared. So that's equation 2. So what we're going to do, we're going to plug equation 2 into equation 1, so it's in terms of time, because both of our questions are going to be asking us for time. So we have now, instead of x plus 22, we're going to write t squared plus 22 is equal to 12t plus a half t squared. And now we're going to solve for t. Now, just giving ourselves a bit more space here to work, the first thing I'm going to do is multiply across by 2. That will get rid of that fraction for you if you don't want to work with it. Just be very careful that you multiply everything by your 2. Then we bring everything over to one side because we end up with a quadratic trinomial. So we want that equal to 0. You're welcome to use your minus b formula. If you want to use guide number, effectively we want to factorize this. So we're going to have minus 22 minus 2. And we get t equals 22 and t equals 2. So we get 2 answers here. Now, usually when we get a quadratic and we're asked to get a time, we tend to have a very obvious right one and an obvious wrong one. That could be a time that's negative, so time can never be negative. Here we seem to have 2 very valid answers. We have t equals 2 and t equals 22. So in terms of the question, we need to figure out, well, which one is correct. So part I asks, after how long will Adam catch up with Ben? So we have 2 possible answers here. So have a think which you might think, which do you think it could be? And actually the answer for part I is t equals 2. And the reason it's that is because both of these answers are valid. Because what this answers is, when will the distance traveled by Adam be the same as Ben plus 22? So basically the question we've asked is, give us the time when Ben and Adam will meet. And why we get 2 valid answers is because they will meet twice. And the second answer actually answers part 2 of this question, which is after how much more time will Ben overtake Adam again. So that happens at t equals 22. So then it's going to be 20 seconds later. Now be careful with how this is asked. How much more time? So it's going to be 20 seconds later, because that happens when the time is equal to 22. Okay, so be careful with that. But both of these answers are valid. They're just giving us the 2 points when it happens. Because in maths, we set it up to ask a question. And the question we've asked it is, tell us when Adam and Ben meet. That's what we're saying. Think of what simultaneous equations really are doing all the time. We're finding where things intersect. We're finding points of intersection. Here we're finding points of intersection, and our point is going to be a distance and a time. So we're finding the time when they meet. So this question gave us both answers with just looking at one approach. So example 3 is from the 2024 higher level exam paper. It's question 1 and part C. So at a glance, this might look pretty much like the question we've just done in example 2, but actually there is a few little tricky parts here that you have to really take care of. So John is cycling on a straight horizontal road at constant velocity 10 meters per second and is 21 meters behind another cyclist, Kevin. So as soon as I see that, I'm going to just draw myself a little diagram here so we can remember that. So John is at 10 meters per second and he is 21 meters behind another cyclist, Kevin. So Kevin, who is cycling at a constant speed of 4 meters per second. So this is the situation. So they're going in the same direction. So John begins to accelerate at 2 meters per second. This is the start of our question. Okay, so this is where time begins for us. So let's just make a VUAST for John. VUAST. So John, so John begins to accelerate at 2 meters per second squared. And he had initially been going 10 meters per second. And we're going to say that that's the time that everything starts. Now, for Kevin, things are a little bit trickier. I'll move this over so we'll end up with a bit more space. So for Kevin, things are a little bit trickier. 1 second later, Kevin begins to accelerate at 4 meters per second squared. So if we look at what happens to Kevin, so we have V, U, A, S, and T. And for Kevin, he was at 4 meters per second to begin with. He was accelerating at 4 meters per second squared, and he starts 1 second later. So it is going to be 1 second less than John goes, well, for the acceleration piece. So he spends 1 second less accelerating than John spent. Okay, so this is our setup. And we want to find the times where John and Kevin overtake each other. So they will overtake each other when they're in the same position. So one of the biggest, I suppose, issues that students could have here is by saying, right, we know that John has to catch up with Kevin. So we're going to take that 21 meters into account, which is correct. However, there is another part. Because Kevin doesn't start from rest, because during that second that we haven't taken account of yet, he has been traveling 4 meters per second. So he's been traveling 4 meters per second for 1 second before we take that information into account. So that means during that time, so think of your distance. It's going to be your speed multiplied by your time. So he travels an extra 4 meters there that we need to take account of as well. And that's the bit that will be easy to lose, because often when we see these questions, if somebody starts doing something a second later, usually they're starting to move, so nothing happens. But because this question started with them both going at a constant velocity, Kevin has movement before this question starts. And because his acceleration section doesn't start for 1 second, he still has that movement, and we still need to take that into account. So let's work with S for both of these guys, John and Kevin. So the distance that John travels is going to be, we're going to use the formula S is equal to UT plus a half AT squared. So that's going to be 10t plus a half times 2t squared, which is 10t plus t squared. Okay, so that's our S for John. So then let's do S for Kevin. And this is only going to be in that acceleration time period. So that's going to be UT plus a half AT squared. Now, we can say that when John and Kevin meet, John will have had to travel the same distance as Kevin, plus have to catch up on the 21 meters, plus catch up on the 4 meters that Kevin traveled during the first second, which we haven't taken account of. Now, another way to look at that is that S for Kevin could have taken that 4 into account there. So what we're going to do is we're going to have 10t plus t squared equals 4 times t minus 1. And I know I haven't done a lot of cleanup on Kevin, so we'll do a half of 2, which is 2t minus 1 squared. And we're going to work this through and get our times. They do ask for both times, so what we assume is going to happen is that John is going to come up past Kevin, but then Kevin will pass John once again. And I nearly forgot our plus 21 plus 4, which gives us that plus 25 there at the end. So just giving ourselves some space, and we add our plus 25 here, we're going to have 10t plus t squared equals 4t minus 4 plus 2 times, let's square that bracket, t squared minus 2t plus 1 plus 25. That's 10t plus t squared equals 4t minus 4 plus 2t squared minus 4t plus 2 plus 25. We have a quadratic, so let's get everything over to one side. So we have a t squared. I have a 4t and a minus 4t, so then I have a minus 10t when I bring that over. And then I have some plus 23 equals 0. We're going to have to use our minus b here. So that gives me t equals minus b plus or minus square root of b squared minus 4ac all over 2a. So that's 2 times 1. And that gives us our two answers, which are 5 plus and minus root 2. And then if we want to break those into decimals, that's 3.6 seconds. And then our second time is going to be t equals 6.4 seconds. So when we see the answer, there's nothing terribly challenging with the answer and the maths, but there is a lot of thinking involved and there's a lot of parts to remember. So the start here about that constant velocity, that should be something that we think about. Why in a question like this are they talking about constant velocity? And the reason was so we could understand that in that 1 second delay before Kevin starts accelerating, that he was still moving and he still did travel a distance. So example 4 is from the 1992 paper. It's question 1 part B. And it's two particles, P and Q, are moving in the same direction along parallel straight lines. Their acceleration are 5 meters per second and 4 meters per second, respectively. At a certain instant, P has a velocity of 1 meter per second and Q is 25.5 meters behind Q, moving with velocity 11 meters per second. So I'm just going to draw myself out a little, just a little sketch to make sense of this. Here is P. P is moving forward. It is traveling at 1 meter per second and it has acceleration of 5 meters per second squared. Q is behind and Q is traveling with 11 meters per second squared, 11 meters per second and 4 meters per second squared, and it is a distance of 25.5 meters behind P. So this is what it looks like. So prove that Q will overtake P and that P will in turn overtake Q. So what we're going to do is we're going to find the times where they meet. And when we do that, we shall get 2 times that are both valid, so positive numbers, and that will prove that Q will overtake P, but they will have to meet again. And the only way for that to happen is that P will in turn catch back up with Q. So let's start with P. So we'll do V, U, A, S, T. And then we'll look at Q. So V, U, A, S, T. So P, we have a lot on the diagram. It's going to be 1 meter per second, acceleration 5 meters per second squared. The time starts at this certain instant, P and Q. So the time is going to be the same for both. For Q, it is moving at 11 meters per second, but is accelerating at 4 meters per second squared. When they meet, P will have traveled some distance, let's call it X, while Q will have traveled that same distance plus the extra 25.5 it needs to catch back up with Q, or catch up with P, because it started behind. So for each of these, we're going to use the formula S is equal to UT plus a half AT squared, and we're going to solve it to find the time where basically they meet. So for RSP, that is going to be UT plus a half AT squared. That gives us X equals T plus 2.5 T squared. For Q, that is going to be UT plus a half AT squared. And SQ is going to be X plus 25.5. That's equal to 11T plus 2T squared. We can bring that 25.5 over. And then we can let the two X's equal to each other. That means that T plus 2.5T squared is equal to 11T plus 2T squared minus 25.5. We now have a quadratic trinomial, so we're going to bring everything over to one side. So minus 10T plus 25.5 equals 0. And if you want to solve it like that, that's perfect. If you want to make it a little bit easier, we can multiply it by 2. That gives us T squared minus 20T plus 51 equals 0. And now we're going to solve that to prove that there are 2 times to answer part 1. So just clearing to give ourselves a bit more space. One of the reasons I like to get rid of any fractions or decimals like that is often we can end up with quite a nice little question. So for here, 51 actually has the factors 3 and 17. So we can get our 2 answers with factorization and no minus b formula. So therefore, 2 overtakes happen. So that's basically what we were asked to prove for part I. So prove that Q will overtake P. So that happens when T equals 3. And that P will in turn then overtake Q again. And that happens when T equals 17. So the fact we're getting 2 valid numbers for time. So part 2 then is when Q is in front of P, and then obviously P is catching up, find the greatest distance between the particles. So that's one of our key ideas, and the greatest distance occurs when the velocities are equal. So that means where VP is equal to VQ. So velocity, we're going to use the formula V equals U plus AT. It's a straightforward one to use, which means VP is going to be U, which is 1, plus A, which is 5 times T. For Q, it's going to be 11 plus 4 times T. That gives us T equals 10. So the greatest distance occurs when T equals 10. However, they wanted to find, well, what is that distance? So what we're going to do is we're going to work out the distance traveled first by P. And we're going to use S equals UT plus a half AT squared. And we are going to use the time as 10. So SP is equal to 1 times 10 plus a half times 5 times 10 squared. So when we get that, that gives us 260 meters. So in the first 10 seconds, so at the point where there's the greatest distance between them, SP, so that means the distance traveled by P is 260 meters. For Q then, we're going to have 11 times 10 plus a half 4 times 10 squared. So that's 200, so 310 meters. So that's the distance traveled by Q. So just be careful. They want us to find the greatest distance between them. But remember that because Q has traveled more, part of that was due to the fact that it actually started behind P to begin with. So we have to take account of that 25.5 meters. So the greatest distance between these two particles is going to be the 310 take away the 25.5 that it needed to catch up, then take away the 260 that P has moved, and that should give us our answer. So we have 310, take away our 25.5, that gives us 284.5, then take away 60, so that means 14.5 meters ahead, and that's going to be the greatest distance. Again, the maths here is really straightforward, but the thinking behind it can be tricky, especially because Q started behind. So when Q is ahead, we have to think of, okay, it needed to catch up 25.5 meters, then it traveled the distance P traveled, then it traveled a little bit extra, so we need to take all that into account. So it is 14.5 meters ahead. So we're going to look at a common initial velocity question. So common initial velocity is one that often throws a lot of students. It's worth doing a bit of practice on. We have a few questions from past papers from the old course that show us how this works. So the hint really is in the name, common initial velocity. So here we're talking about questions where we have different stages. But unlike our velocity time graphs, we have just one acceleration throughout the whole question. So we use velocity time graphs when we have different sections and each section has a different acceleration or deceleration, or in some cases, no acceleration, it's constant speed. But in these questions, we will still have the sections, but we're going to see that that acceleration doesn't change. So because of the way that they're set up, it's very easy for students to kind of maybe approach this in quite a difficult way. But the key idea here is that in order for us to correctly find every piece of information we need and to do that efficiently, we need to keep bringing our sections back to the start. Okay, and that's so important. So let's take a look at an example to illustrate this. These questions also appear in our vertical motion with vertical motion. So we have common initial velocity with vertical motion, and I have covered this in the vertical motion video, which is linked in the description below. So if you want to see this in action in another way. So example 5 is from the 1996 higher level paper. It's question 1 part A. So particle starts from rest and moves in a straight line with uniform acceleration. It passes 3 points, A, B, and C, where AB is equal to 105 meters. The length or distance between A and B is 105 meters, and then the distance between B and C is 63 meters. If it takes 6 seconds to travel from A to B and 2 seconds to travel from B to C, find its acceleration and the distance of A from the starting point. So the first thing I'm going to do is I'm going to draw this out. So we have a starting point here, and then we have particle moving in a straight line with uniform acceleration, and it passes 3 points. So we have A, we have B, and we have C. So what we're told is A to B here is 105 meters. And we have B to C, which is 63 meters. And it takes 6 seconds to do the A to B section and 2 seconds to go B to C. So we're trying to find the acceleration and then the distance from A to the starting point. So this section here is what we're being asked for in part 2. So how we would identify this as a common initial velocity question is the fact that there are multiple sections, but the acceleration is the same, and we don't know that. Generally, these questions also have an unknown initial velocity, which is true here. You might say, well, we know the particle starts from rest. Yes, we know the particle starts from rest at its starting point, but we don't know where that is. So we have to work with the sections that we have. So the first section we're going to work with is AB. So I'm going to label these with a subscript 1, VU, A, S, T. And that is going to be an unknown U. So I'm just going to call that U meters per second. An unknown A, so A meters per second squared. It travels 105 meters, and then the time is 6 seconds. Now, because we have two unknowns, we're going to have to create two equations and work with simultaneous equations. Now, the common mistake, so I'm just going to show you what's incorrect. The common mistake students do is they look at B to C, and then when they do their VUAST, the problem is they have some information and they are missing other bits. But the problem is U is not U here if we start at B, because U, the start of the velocity or the initial velocity at B, is going to be different to U, the initial velocity at A. So we end up having to introduce a third unknown effectively, and we don't have enough information to solve that. So we could think about this V of this section becomes U here, but that's so overcomplicated. We want to keep this super simple and work this as efficiently as possible. So the trick for these questions is that we have to bring back any section to the same starting point, which means instead of BC, we're going to work with AC. So we extend that first section. And doing that simplifies the whole question. And it means that we now have a U, because it starts the same point. The acceleration is still the same. S is no longer going to be 63, but we do know what happens A to B. So we can combine these and get 168 meters. And then our time is going to be a combination time, and that's 8 seconds. So we're going to use S equals UT plus a half AT squared to create two equations. And once we create those equations, we're going to solve them simultaneously. So let's look at section 1. So that's S is 105 equals U times 6 plus a half A, which we don't know, 6 squared. That gives us 105 equals 6U plus 18A. I'm going to simplify that by dividing it down by 3. That gives us 35 equals 2U plus 6A. So working with section 2, I get S 168 is equal to U times T plus a half AT squared. So 168 equals 8U plus 6432A. This can be divided by 4, but actually this can be divided by 8, but I'm only going to divide it by 4, because if I divide it by 4, we are left with a 2U again. So it saves us doing any major work with our simultaneous equations. So I'm going to just flip these around. I prefer to have my constant on the right hand side, but it really doesn't matter. And then I'm going to change the sign of the second equation. So that's going to be minus 2U minus 6A is equal to minus 42. Working that through, we get minus 2A equals minus 7. So A is equal to 3.5 meters per second squared. We then go back and we have 2U is equal to 35 minus 6 times A, which is 3.5. So I've just rearranged equation 1 slightly. You can go back to the initial one, the initial equations, but those numbers are very big. So we get 2U, 6 times 3.5 is 21. That gives us 14. So U is equal to 7 meters per second. We were not asked for U. We were only asked for the acceleration for part 1. However, for the second part, the distance of A from the starting point, we will need that initial velocity, or at least thinking about that in terms of the second question, we want the velocity at A. So just giving us a bit more space to work for part 2, we're looking at the section here at the start. So this part here. So if we set up our VUAST again, let's think about what information we have. So because there's the same uniform acceleration throughout, we've just worked that that's 3.5 meters per second squared. We're trying to get the distance. So we're thinking of this from the start to point A. Okay, so that's the section that we're dealing with. So we know that this particle starts from rest, and we've already worked out the speed or velocity when the particle is passing A. We worked that out as our U, but for this section, It's our final velocity, so it's our 7 meters per second. So we actually have all the information we need now, and we're going to work with the formula without t. So that's going to be v squared is equal to u squared plus 2as. That gives us 7 squared equals 0 squared plus 2 times 3.5 s. So that gives us s equals 49, and that's divided by 7, which gives us 7 meters.